Okay, so in this video, we're going to be continuing with our discussion of probability distributions, and we're also going to be thinking about how they map onto the central limit theorem so that we can calculate or think about things like confidence intervals and things like that. So we're going to be taking some random samples from distributions, and we're going to be graphing them and seeing how they change based on the size of the samples that we take. And then we're also going to be looking at essentially bootstrapping, looking from sampling within a given data set and how that will also map out onto the central limit theorem. So we're going to start by looking at the elements that we're going to use to build our loop first for our repeated samples. So we're first going to take a single sample, and we're going to use the R norm function. So we're going to take 100 samples. From our normal distribution. We're going to give it a mean of 500 and a standard deviation of 100. This is typically what you would expect on one test within an SAT test. So that's where those numbers are coming from. For instance, on the English test or the math test, specifically the subtest, on that subject, the mean would be 500, standard deviation of 100. That's what gets you 200 to 800 range of scores. And so if I run that, then I have a sample here. There's 100 outcomes, and you can see the sample scores here. Now, I can calculate the mean of those samples. And the mean that I get here is just a value. It's 492 in this example. So that's pretty close to 500. And then what I want to be able to do for the loop is to collect these means into a vector so that I can then plot the mean of my samples. So to do that, we're going to create a vector that for now is just empty. And then I'm going to specify the number of sampling steps that I want to take, how many samples am I taking, and then also how big my samples are. So for this example, I'm going to have each sample be 100, and then I'm going to take 1,000 of those samples of 100. And then my for loop for I in 1 to n, curly bracket, sample R norm, helps to spell, n mean equals 500, standard deviation equals 100. And then I'm going to take the mean sample, and then I am going to stick that into my means. And what I can do to do that is I can take my means vector that exists, and by putting it in another vector with a new value on the end, that's essentially going to make a vector of the vector that I had plus the new value. So you can think of this as a method of appending a value onto the end of my vector. And then once I have that all in place, make sure that I've installed my numbers n and n, and then I can run my for loop. And again, depending on how big your samples are and how large your sample is for each thing, this didn't take very long on my computer for this example, but if you're doing very large samples or doing very complex calculations in your loop, it might take a second. Now, once we have the data in our means vector, and we should be able to see our means right here. It's got 1,000 samples in it, and here's our means that we got from each of our runs. We can now then plot a histogram of our data, the means. We're going to give it a title. Histogram of sample means for SAT simulation. XLab equals sample means, and YLab equals frequency. And we can run that. And so this is our histogram of the data that we simulated. You can see it looks very normally distributed, which is about what you would expect since the underlying distribution is also normal. We can also calculate the mean of our means, which we would expect to be very close to 500. And we can also calculate the standard deviation of our means. Now, recall that for the standard deviation of the sampling distribution is the population standard deviation divided by the square root of the sample size. And since our population standard deviation was 100 and our sample size was also 100, the square root of 100 is 10, 100 divided by 10 is 10. And so this is actually close to what we would expect it to be from the theory. Now, standard deviations don't follow a normal distribution, but instead follow a chi-squared distribution. So we can actually do a example of that as well. Now, when the sample is, when you take a lot of them, the degree, depending on the degrees of freedom, the histogram may not appear very skewed. But if the sample size is very large, particularly for our example of 100 samples, the central limit theorem will tend to take over, and you will still end up with a relatively normally distributed outcome. But we can follow the same model that we did for the previous example. We create our empty vector. We still specify n is 1,000. And then n is 10. So to see a little bit more of the skew, we're going to take a slightly smaller sample size. And then for I in 1 to n, we're going to do our sample, our norm, n mean equals 500. Standard deviation is 100. And then the standard deviation, we're going to take the standard deviation of our sample. And then standard deviations vector, we will tack on the new standard deviation. And so if we run that, awesome. And then we can plot and see how we do. Main equals histogram of sample standard deviations for SAT simulation. XLab sample standard deviations, and y lab equals frequency and we can run that. And so that's our plot of the sample standard deviations. This title went a little too long. If you want to break it up into 2 lines, you can put a carriage return in there. Looks a little nicer. And we can also calculate the mean of our standard deviations from our sample. Which is 97. And you can see again, that is close to the 100 that you would expect it to be from each individual observation, the mean of our means, the mean of our sample standard deviations. Now, for the binomial, because the observations are already discrete and we don't have to work quite as hard for the normal distribution sample, we don't actually need to construct a loop in order to do a simulation of the binomial distribution. We just need our binom. So n equals 1,000, n equals 100, because each time we calculate the binomial distribution, it's already a collection of samples because we're flipping the coin repeatedly. So for this example, I'm going to set the probability equal to 0.3. And we can do a proportion sample with our binom n, n, and p. And if we want to calculate it as a proportion, then we're going to divide it by the sample size in order to get a probability rather than a count. And I can run that. Oops, I forgot to run my other things. There we go. And then we can also make a histogram of that. Histogram of sample proportions simulation. X lab is sample and Y lab is frequency. That's my frequency. This is the proportion. And we can calculate the mean of our proportions, which again should be around the same proportion that we had to start with, and the standard deviation of the proportions. Now, where did the standard deviation come from? The standard error for a sampling distribution is the proportion times 1 minus the proportion divided by n, and then take the square root of the whole thing. And so that, for this 0.3 calculation, calculates to about 4.58%. And I got 0.4599%. So again, it is very, very close. Now, from this data, if I want to calculate a confidence interval based on my simulations, I can do that. I can do that by first sorting my data. So I'm going to do this on the proportions example, but it will also work for the mean simulations and the standard deviation simulations we were doing earlier. So I'm going to create a new vector, my sorted proportions in this case, and I'm going to sort my proportions. And then since I have 1,000 observations in this data set, that 2.5% of 1,000 is 25. So the 25th observation will be the bottom end of my confidence interval. And then the top end would be on the flip side. And you can do 976 or 975. It's the 900. Remember the probability is 97.5%. And you want to be at or above that. And so I just chose the above that and 0.39. So my confidence interval on this sample proportion would be between 0.21 and 0.39. And again, you can do this similarly for the means or the standard deviations examples we did earlier in order to obtain the confidence interval. Now, if your samples are not 1,000, then obviously you would take your 2.5% and your 97.5%, you would multiply by the sample size in order to get the position in the list that you were looking for. Now, we can also do a similar trick if we want to simulate sampling from an existing data set. So I'm going to import a package called dplyr. And we're also going to look at the mtcars data set as our sample, as our packet, our data set that we're going to sample from. And we're going to create a similar loop that we created before, but we're going to sample from this data set. And that's why we needed the dplyr package, because it has a nice sampling function for sampling from within other data sets. So our code is going to be very similar, except for that. So we're going to have our empty C vector, and n is 1,000, and we're going to take a sample of 10 for our simulation. And then for I equal, or I in 1 to n, curly bracket, our sample will be from the sample n function, which is what I needed dplyr for. mtcars is the data set. I'm going to take n samples, and I can either do replace equals true or replace equals false. If you set replace equal true, this is essentially a bootstrapping example, because it allows you to select the same thing more than once. Mean is going to be the mean of our sample. And this is sampling the entire observation. So I'm just going to calculate the mean of the MPG, not the entire data set, just the mean of the MPG. And then I'm going to collect the means of my means. All right, and let's run this. And notice that took a second. And now we're going to make a histogram of my means. And there is my sample means from my simulation. And I can calculate the mean of my means. And I can calculate the standard deviation of my means. And I can compare that to the mean and the standard deviation of the original variable. And you can see that the two means are very similar to each other. The true mean of the data set is 20.09, and I got 20.01 for my samples. The standard deviations are different, but remember that the standard deviation here is the population standard deviation, which is the 6.2, divided by the square root of the sample size. So if I were to take my 6.02 and divide it by the square root of 10, I actually get 1.905 something. And so this is going to be 1.85, so it's a little bit lower, but it is still in that ballpark of where you would expect it from the sampling distribution. Now, if we want, we can create a function that will do a lot of this for us, and we can simply specify some of the parameters and use the function that way. So for instance, we can specify in the comments so that we understand what's going on here. N is the number of samples. Little n is the sample size. Mu is the population mean. And sigma is the population standard deviation. So we're going to sample from the normal distribution for this function, and we're going to specify a function with inputs n, mu, and sigma. And what are we going to do? We're going to open a empty means vector, and we're going to create a for loop, I in 1 to n. We're going to take our sample, our norm, and we're going to take our sample size, and we're going to take our mean equals mu, and SD equals sigma. And then we're going to calculate the mean of the sample. And then we're going to calculate the means by appending our new value to the means vector. And that's the end of our for loop. And then before our function ends, we're going to print the mean of the means. And we're also going to print standard deviation of the means. And we're then going to also make a histogram of the means. Main equals histogram of sample means for SAT. Well, we'll just say simulation. The values we used are in our example are for SATs, but we'll be a little bit more generic here. X lab is sample means, and Y lab is frequency. And so that's the end of our function. We're going to load all that into memory, and then we can actually run the function by just specifying our total number of simulations, our sample size, our mean, and our standard deviation. And then this will simulate our SAT. If we wanted to change, we could do 10,000. We could do a sample size of 5. We could do, let's say, IQ scores. And again, we've printed out to the screen our mean of our means, and our histogram appears already pre-labeled. So if you're going to be doing a lot of these simulations, it's always a good idea to collect everything in one place so that it's easy to use.